Chapter 12, Chemical Reactions. One of the first quantity that we encounter as soon as we began to study chemical reaction is phlogiston. What is this quantity? Two German chemists, Jonathan Becher and George Stahl, developed the phlogiston hypothesis. According to the phlogiston hypothesis, all substances that can be burned contain phlogiston. As the burning takes place, the phlogiston leaves the substance only when air is present to absorb it. Now we know that this phlogiston theory is incorrect. The phlogiston hypothesis was wrong. And now we begin to understand what really is happening during the chemical reaction of combustion. Okay, so we'll go on. Phlogiston disappointment. The 17th century French chemist Antoine Lavoisier performed experiments that rejected the phlogiston theory. Lavoisier placed tin inside of an evacuated region and floated it on water and focused a beam of light onto the tin. After some time, he now realized that some chemical reaction has occurred. As we can see, there's a change in the substance. So tin is still here, but this is tin oxide. Okay, and now the whole system uh, uh, floats lower than it did before. Water has risen on the inside of the uh, uh, beaker, the inverted beaker. Okay, so this helped to show that the phlogiston theory is incorrect. Now, oxygen, which is needed for combustion, that will come later. The English chemist Joseph Priestley discovered a gas that Lavoisier later named oxygen. When oxygen combines chemically with another substance, the process is called oxidation, and the substance is said to be oxidized. Okay. Now let's also deal with air, because air, we will find later, is important for combustion reaction to occur. The fresh air contains mostly nitrogen. About 78% of the air is nitrogen. About 21% of it is oxygen gas. These are both gases, nitrogen gas, oxygen gas. Or argon gas is next, and carbon dioxide is only 0.3%. And there are other gases in much smaller quantities. But the important feature in this context is oxygen is present in the atmosphere. Oxides. An oxide is a substance that contains oxygen and another substance, such as carbon monoxide, sulfur dioxide, etc. In general, the oxides of metals are solids. Oxides of nonmetal may be solid, liquid, or gases. Now, a mole. How much is present is what a mole answers. A mole of any element is that amount of it whose mass in grams is equal to that substance atomic mass expressed in U's or times U. That is to say, 1 U is 1.610 to the minus 27 kilograms, 1.610 to the minus 4 grams. So if you think about then, different substances then, because they have different atomic masses, will have a different mass for the same amount of moles. So an atom of carbon has a mass of 12 atomic mass units. A mole of carbon then has a mass equal to 12 grams. An atom of oxygen then has a mass of 16 um, uh, atomic mass units. A mole of oxygen then has a mass of 16 grams. Now, formula mass is important as well. So let's take sodium chloride. For one sodium atom, the mass of that atom is 22.9 times U. For chlorine, the mass of a single atom is 35.45 U. So the formula mass then for sodium chloride is 58.44 U, the sum of the two. Try another formula. This is sodium sulfate. We have 2 sodium atoms, 1 sulfur atom, 4 oxygen atoms. So that will be 2 times the atomic mass for sodium, 45.98, on and on and on. And we finally get a formula mass of 142.04 units. Okay. Uh, Mass relationships in reaction. Here we're going to react propane, C3H8, with oxygen, and we'll end up with carbon dioxide and water. So 1 mole of propane plus 5 mole of oxygen yields 3 moles of carbon dioxide and 4 mole of water. Each one is the coefficient of that particular substance. An exothermic reaction now, a chemical reaction that gives off energy, those reactions are called exothermic reaction. And one such reaction is the neutralization process is an exothermic reaction. Carbon plus oxygen yields carbon dioxide and energy given off, with E equals 9 kilojoules per gram of carbon dioxide that is produced. An endothermic reaction is just the reverse. A chemical change that absorbs energy are called endothermic reaction. And dissociation of a substance is a endothermic reaction. It takes energy to drive the process of breaking water in this dissociation into hydrogen gas and oxygen gas. Endothermic reaction and exothermic reaction compared. If a chemical reaction is exothermic, meaning pushing to the right, then the reverse reaction would be endothermic, the process being driven to the left. 1 point. And the amount of heat liberated by the exothermic reaction must be the same as the amount of heat absorbed by the endothermic process. Endothermic and exothermic reaction illustrated here. Here the chemical reaction proceed from top to bottom. The combination of adding carbon and oxygen gives off heat, ending up with carbon dioxide. This one proceed from bottom to top, and you have to absorb energy in the process to end up with nitrate oxide. Chemical energy and stability, which is an important concept also. The more energy needed to decompose a substance, the greater the chemical stability of the substance, with a few exceptions. This illustrates energy and chemical bond. Notice that there is an illustration of potential energy here in this book raised above the table. And this is an illustration where the energy has been released when the book now is back on the table. Chemical energy and stability continues When electrons move to new location during an exothermic reaction, the original potential energy is liberated or released. The freed energy may show itself in faster atomic or molecular motion that correspond to a higher temperature, or the freed energy may excite outer electrons into higher energy levels from which they return by releasing photons of light. A continuation. In endothermic reaction, energy must be supplied to the atoms involved, as we've said, to enable some of their electrons to form bonds in which their potential energy are greater than before. And now chemical energy is electron potential energy. That's a fact that you need to know. Activation energy is an important concept. In many exothermic reactions, the reactant must be activated or supplied with sufficient outside energy to make the reaction start. The energy needed to start a reaction is called the activation energy, and a molecule having enough energy to react is called an activated molecule. This is an illustration. Before the car can get to the bottom of the hill, we have to put energy into the system, which is thought of as activated energy. But once that energy is there, then that energy can be liberated as the car rolls down this hill. Concentrations and surface area. Reaction rates of simple chemical reactions are proportional to the concentration of the reactants. Reaction speed depends upon the amount of solid surface they expose. The greater the surface area, the faster the reaction. And finally, then, um, uh, catalysis. Uh, a, a catalyst accelerates reactions in different ways. Two of the ways. A catalyst forms an unstable intermediate compound with one of the reactants which decompose later into the reactants. And two, the catalyst increases the reaction rate by producing activated molecules at its surface. Okay, that is the end of this presentation.